Hello everyone. Hello everyone. My name is Antonio Coleman and I would like to welcome you to my second installment of my newest series where I cover various data structures and algorithms within the field of computer science. In the last video, I discussed an introduction into red-black trees, and if you missed that video, I would highly encourage you to watch the video before this and then come back to this video after. To catch up on the previous video, I would summarize it best by the overview of the acronym BSTs and what they stand for, which if you don't remember is completely fine, but it stands for binary search trees. Additionally, I went over how they work and how their pitfalls can be negated by implementing red-black binary search trees. If you forgot the context of this question or the answer to it, that's no worries as well. The answer for this is that red-black trees offer self-balancing properties. And lastly, I also went over how red-black trees work by self-balancing, as well as some of the real-world use cases for red-black trees and how they provide solutions that make things as complex such as database indexing to things that we use every day like spell checkers and automated autocorrect systems work. Now let's get into the content of this video. The first concept that we will be going over is time complexity. For red-black trees, the time complexity for all major operations such as search, insertion, as well as deletion work at a reliable O log n. Now, if you are unsure of what this means, or if the idea of time complexity is confusing for you, don't worry. I understand how overwhelming it may be at first, or how it can feel to not understand why it is important. So here we go. Let's begin by reviewing Big O notation. Big O notation is best described as a computer science tool that describes the time and space complexity of algorithms. Now, if that sounds like a lot for you, don't fret. I'm going to give you a real-world example that might help contextualize and reinforce the importance of time complexity and how it works within its operations. For the sake of this argument, imagine you have a bakery that you own, and your job is to fulfill orders for cookies. For the sake of this example, let's represent cookies with n. Here, time complexity is essentially how long it takes to complete an order from start to finish, but more specifically, how time changes as the quantity of cookies goes up. Now, since it has been established that O log n is the reliable time for all operations within red-black trees, we can think about red-black trees as self-balancing cookie trays. Here, they work as self-balancing cookie trays that no matter how many cookies get ordered, the pile never stacks up in a sloppy or non-organized manner. Additionally, to explain O log n, let's continue with the cookie example. Here, O log n helps you search inventory, add cookies, or remove them as you please from the tray stack. If you ever want to double the amount of cookies, you don't have to undergo some difficult or long process each time. This may look something like going from 50 to 100 cookies by just adding one single tray. Now let's go to operations like searches, insertion, and deletion. Let's first begin with searches. Let's say for your bakery, you need to find a customer's order. For this example, let's call the person John. And your mission is to find John's order amongst the hundreds or even thousands of other orders that you may have as well. Now, while at first you may think that you have to search each tray one by one to find the cookie order that he placed, this is not the case and is rather ineffective for time. Due to this slow process, it will be much easier and sustainable to offer searches. Here, searches will allow you to look at the middle of the tray, take the client's name, which here is John, and see if it comes before or after the surrounding cookies on the tray. Now, you can easily discard the half of the stack that you do not need, cutting your process in half and saving you time. Next, how about we talk about insertion, which would be like adding cookies. which in computer science will symbolize nodes. Here, we're looking to add nodes or cookies to the existing stack. Let's say, for example, you need to take an order that requires a fresh lemon swirl for Mark. Here, you must find the exact alphabetical correct position to place this new order. Additionally, let's differentiate this order from existing cookies by adding a default red flag. However, what happens if there's another cookie order with around a similar red flag to this one? That would be pretty confusing, right? For this example, we will have to rotate a few trays and restructure the stack without making it too tall, because that violates a rule. Here, we don't want to make the stack too tall because we still have to flip the organizing flags from red to black and vice versa. Lastly, let's cover deletion. Deletion is exactly what it sounds like. Here, it would be the removal of cookies. For this example, you must locate the target that you want to remove. For example, this could be searching for a vanilla bean that you want removed. Normally, this will require you to physically remove the order from the trays, and also you would have to remember if the cookie removed had been replaced by another cookie. With deletion, you will be able to remove the replacement cookie as well. However, one problem that you might encounter is when you remove a cookie with a black flag. The problem here is that when you remove a cookie with a black flag, this violates the black height rule of the stack, which makes the path shorter and also puts the stack out of line, which you do not want. To fix this issue, you restructure the trays to redistribute the number of black flags on the path. Now, you must also flip the flags to satisfy the black height count. This effectively solves your problems. Lastly, here are my resources, and this is the final section of the video. I would like to thank Geeks for Geeks for their resources, as well as my professor, Dr. G, for instilling this information within our lectures. Thank you. I hope you enjoyed the video. I hope you found it helpful, and I hope you tune in for the next installment. Thank you.